Welcome back. Good morning and hello, everyone. We continue with another exciting session of our school workshop, which is the second part, more advanced part of our summer event, Quantum Horizons, Developments and Opportunities. It is my pleasure to inform you that our first speaker in this session is Professor Angelo Bassi from the University of Trieste, a wonderful scientist and a wonderful person. Research fields of Professor Angelo Bassi include quantum mechanics and its foundations, the measurement problem, the meaning of the wave function, entanglement and non-locality, the quantum to classical transition, the relation between quantum theory and relativity gravity. He has kindly agreed to join us for this school workshop, and he's going to talk all about spontaneous wave function collapse models and introduction. Angelo, please come.
Okay, thank you. So I hope you can hear me well. And so thank you very much for the invitation and also for the very kind introduction. It's a pity that we can only meet online. Actually, I mean, I was invited to come to Turkey 2 years ago. There was not the school organized in March 2020, but then the pandemic broke out and I couldn't come, but I hope that one day I will. So far we will meet and discuss online.
Sure.
So as you kindly introduced, so this my talk and my field of research is on the foundations of quantum mechanics. So to understand the meaning of the theory, the problems that it has, possible solutions, and this is basically the content of my talk, and which fits well with the title Quantum Horizons. So it's one of the horizons of quantum theory and the futures of quantum theory. So let me see. Okay, so what is first the motivation for collapse models. So what is there is a problem with quantum theory, and what is the problem with quantum theory? If you take the standard version of it, the one that you don't find so much in modern textbooks, but it was clearly spelled out in older textbooks, quantum theory divides the world in two parts, in fundamentally two different parts. There is the quantum world, the one that we are talking today, the one quantum theory is about, the world that originally was the world of atoms, molecules, particles and subatomic particles, but now it's extending more and more to complex systems and eventually also the entire universe. But at the beginning was the microscopic world, which is governed by a wave function, which I'm showing the equation, you know all these things. But then there is also a classical world. There is a classical world of apparatus and measurements, and they use the wave function to predict properties about the microscopic world. So this is the fundamental distinction, which was clear in the mind of people like Niels Bohr, Heisenberg, Born, and the entire Copenhagen school, although with differences among the different people. And it's also spotted out in this quote by Steven Weinberg, which I like to quote from time to time. So the Copenhagen interpretation assumes a mysterious division between a microscopic world and governed by the laws of quantum theory, and the macroscopic world governed by classical physics. And observers and apparatuses. And there is no clear distinction between them, the one and the other. There is no clear rule to decide when you go from one to the next. So this is very well okay from a phenomenological theory of nature, but it's not good for a fundamental theory of nature as quantum mechanics seems to be so far. So this division should be explained or should be removed. You should do something about that. And this is a problem which has been debated over the decades, is a fundamental problem. It's not a practical problem. Quantum theory works very well for all practical purposes. Now we have newer and newer quantum technologies. So the issue is not about the applicability of quantum theory, but it's about the foundations of the theory. It's about understanding the meaning, what the theory is telling us about the world, the physical world, especially at the microscopic level. Okay, next. Okay, so where is the root of the problem? The root of the problem is, of course, in the superposition principle, the possibility that quantum system can be at the same time in the superposition of two different states, like typical example, atom here plus atom there. And this quantum superposition, I'm telling simple things to start with, things that you all know. These quantum superposition have been verified experimentally at the microscopic scale with extremely good accuracy, an incredible number of times. So double slit experiments, diffraction experiments, and everything you can think about. Basically, in general, all the technologies, quantum technologies, are rooted in the quantum superposition principle in a way or another. But what is the issue? The issue, again, I come with the problem with the theory. The issue is that if you take the theory seriously, when you couple a quantum system, which is in a superposition with a macroscopic system with a macroscopic object, also the macroscopic object, according to the theory, goes in the quantum superposition. And this is the essence of the Schrödinger cat's paradox. If you put the cat in a box, as Schrödinger said, with a mechanism which might trigger some poison or might not, depending on a radioactive decay process, then if you describe the system quantum mechanically, the superposition of the atom being decayed or not turns into a superposition of the cat being dead or alive. Dead and plus alive, the superposition at the same time. So this is the theoretical description. And then the theory says that only when you open the box, you should see one of the outcomes. But even if you consider yourself as a physical system, not as an observer, a system made of atoms, if you open the box, you also go in a superposition of seeing one thing and the other thing. If you take the environment into account, also the environment goes in a superposition of interacting one way, interacting in the other way. And eventually, if you want really to push things very hard, you have the entire universe, which is in a quantum superposition of all possible states, and then you cannot take one of them out as the reality as we see it. And this actually is the problem of quantum cosmology. In quantum cosmology, you have a universal wave function, which in principle is completely homogeneous and completely symmetric, because this is the initial condition of the universe. And then why do we see the world as we see it? So there is a problem. Again, it's not a practical problem. You can always find ways to cope with the problem, but it's a fundamental problem. And since we are talking about a fundamental theory, one has also to deal with these fundamental problems. Okay, so there are many ways to cope with the problem. So the problem is the linearity of the Schrödinger equation. So why superpositions do not invade our world, our macroscopic world, but we are always in a definite state? Why don't we see a quantum world? Why do we see a classical world if everything is quantum? And again, I want to stress that many times it's said that decoherence is the cause of that. No, I mean, in a practical way, yes, the coherence in a practical way explains some things. But at the fundamental level, the coherence doesn't explain it, because the coherence is just interaction among physical systems. And if the system is quantum, everything is quantum, everything is in a crazy, highly entangled, completely non-classical superposition, and then you have to understand how classicality emerges out of that. So there is a problem. There is a consensus in the community working on quantum foundations that there is a problem in understanding the theory. Now the issue is about the solution to the problem, and I will propose one of them. So again, one slide, just to quote, I mean, among the many people, to quote Nobel Prize winners that are aware of this problem. So Einstein, of course, famously, always he was concerned about the meaning of quantum theory. And he was convinced that it's not the end of the game. It's certainly there is truth in quantum theory, but it's not the end of the game. But more interestingly, also in present days, the Nobel Prize winners like Weinberg, like Penrose, like Leggett, question the fundamental validity of this theory. And again, I mean, just to quote a Nobel Prize winners. Okay, so a solution that I want to propose here that is called the models of spontaneous wave function collapse. And the idea is very simple. So if the problem is to explain why quantum superpositions, why the linearity of the wave function seems not to propagate to the macroscopic world, we never see ourselves in a superposition. So the idea is to violate the superposition principle, to modify the Schrödinger equation in such a way that the superposition principle is fundamentally wrong. It's practically good at the microscopic scale. It's not good at the microscopic scale, but the fundamental theory is a nonlinear theory of nature. And actually, if you think carefully, it's kind of surprising that superposition, so the linearity is a property of the theory. Linearity is a very special property. Nature in general is not linear. classical mechanics is not linear. Electromagnetism is linear, but only the electromagnetic waves. If you put matter in the game, it's not linear anymore. General relativity is not linear. In general, only probabilistic theories are linear, but fundamentally, the other theories of nature are non-linear because linearity is a very unique property. So why nature should have chosen that unique property in place of just any other? So it's in some sense, it's very natural to think that the linearity of quantum theory is a weak field limit, whatever, is an approximation of a deeper level nonlinear theory. And collapse models aim to give a glimpse, give a hint about that fundamental theory. These are models, it's not a new theory of nature. They just want to go behind standard quantum mechanics. So the goal of these models is to modify the Schrödinger equation, to introduce nonlinear terms in such a way that at the microscopic level, you keep quantum mechanics. It's still there, but then you have the quantum to classical transition at the macroscopic level. Instead, you have the wave functions are always well localized in space. So well localized in space that they behave for all practical purposes like particles. That is the moral of that. So in a sense, it's a unique quantum world. There is no division between quantum and classical, but there is a transition which is explained by the dynamics of the model. It's a transition between one regime, the microscopic one, and another regime, the macroscopic one, described by unique dynamical equations. This is the goal, and they achieve it, of these models, which were first proposed in 1986 by Gerhardt and collaborators, and then have been developed by several other people around the world. Okay, so just at least in one slide, I would like to show the typical equation that we deal with, the dynamical equation of collapse models. So it's the one in the box. And then if you want, there is the reference to a physics report where, and the review of modern physics, where we summarize all the results that I'm going to talk about. So this is an equation for the wave function. Psi is the wave function of a system because it's a quantum theory, so there is a wave function. The term in blue is the standard Hamiltonian, so that would be the Schrödinger equation. There you have all the interactions that you want to deal with. You have also linearity, so the blue part is linear in the wave function, but the red part is the collapse dynamics, which is non-linear. So you see that there that so an operator appears, M. M is the mass density operator. You see it there in the middle left. The capital M, the operator is just small m, the mass of the particle. If you can see my cursor, this is the mass of a particle, and that's A daga A are the creation and the annihilation operators of usual second quantization. So this is a density. A daga X, AX is the density, particle density. If you multiply by the mass, is the mass density. And here, both words are important, both mass and both density. Mass, because you want to make the model mass proportional. The more massive the system, the stronger the effect. So that's why you take the mass density. You take a density because you want to distinguish different positions in space. So if you take a density, then the structure there is capable of collapsing superpositions in space, here plus there. If you had only the total mass operator, for example, it wouldn't work. You need a density in space in order to collapse in space. So that's why you have the mass density operator. Then there is a noise, Wt of x, the one over here, is a noise, is a white noise, basically. It's white in time. And it is white in time simply because the equation is simpler if the noise is white, otherwise it becomes messy, but you can still work with that, but it's easier to take it white. And here you have the correlation in space. So you see that in space, there is a spatial correlator, G, capital G, and I will tell you more about that later. The mean is 0. So there is a noise. It's a stochastic evolution because the collapse occurs randomly in space. You don't know where it occurs randomly. And then it's a non-linear equation because the wave function enters in the red part, enters 3 times. So it enters twice here, because you want to take the expectation value of n, and then it enters also here. So it's 1 time, 2 times, 3 times. So this is a highly nonlinear and stochastic equation. And it has to be like that. Nonlinearity, you need the nonlinearity because you want to violate superposition, you want to collapse superposition. So the equation has to be nonlinear. It has to be stochastic because the collapse process is random. So this is the equation. You see that the new terms look a bit long, a bit ugly, again, because this is a model, it's a phenomenological model, it's not a fundamental equation. But this is the equation, oh, sorry. This is the equation that we deal with. So with this equation, you can describe basically all collapse models, and in the literature, 2 of them have been considered in particular. One is the CSL model. CSL stands for continuous spontaneous localization, which was proposed by Pearl and Girardi in the early 90s, late 80s, early 90s. And basically the correlator, I mean, the structure is the same. The important degree of freedom is the spatial correlator, which has been supposed to be Gaussian. You have a Gaussian correlator over space. The width of the Gaussian is controlled by RC, which is one free parameter of this model. And then lambda is the strength of the collapse. M0 is the reference mass, is the nuclear mass. This is just to set a scale. So lambda sets the strength of the collapse. The stronger lambda, the stronger the collapse. RC instead, I will tell you now, is a spatial resolution of the collapse. Then there is the DP model. DP stands for Dioschi and Penrose. The structure is the same, and the correlator is 1 over R. And the one nice feature with the capital G is the gravitational constant, H bar is H bar, of course. And so there are 2 nice features of these models. One is that, in the DP model, the collapse is somehow related to gravity because you have capital G. And there are no free parameters so far. So in the CSL model, you have 2 new parameters, lambda and RC. And here, so far, you have no free parameters. Okay, so this is the equation. So of course you have, I mean, it takes a lot to work to understand these equations. I mean, it's part of the expertise of people working in collapse models, but there is a nice way to understand the physical content of that equation, which somehow I already anticipated. So we take the following situation. Suppose that you have a microscopic system in a superposition here plus there, superposition in space. The mass of the microscopic system is small, it's a small mass. The mass density is small. Therefore, the collapse is weak. It is there mathematically, it's in the equation, but it's extremely weak and negligible for all practical purposes. The microscopic system will be in a superposition, will continue to be in a superposition for a very long time. You can do interference experiment and you will see interference as we see in laboratories. So the quantum dynamics dominates over the collapse dynamics. Of course, there are some tiny collapse effects, but they're very small and you have to really look for them. And this is something that people are doing, and I will tell you in the second part of my talk. Take then a macroscopic situation when you have many atoms like the Schrödinger cat or whatever, a table, a chair, whatever, in a superposition here plus there. Well, then now the situation is completely different. So qualitatively, it's the same. It's always a superposition. It was a superposition in the microscopic case. Now it is in a superposition in the also in the macroscopic case. So qualitatively, the situation is the same. But from the quantitative point of view, the situation is entirely different. Because before, when you had only one atom, there was a small mass density. Now, when we have the Schrödinger cat, it's a much bigger mass density. It's 10 to the 24, whatever, Avogadro's number. It's 10 to the 24 times stronger mass density than before. And now if you plug the numbers into the dynamics, you see that the opposite occurs with respect to the previous situation. Now the collapse dynamics is stronger than the quantum dynamics. And the collapse dynamics forces the wave function to collapse somewhere in space and to remain collapsed in space. So the Schrödinger cat will never be in a superposition here plus there, dead plus alive or whatever. There will be a unique classical configuration. It will be a wave function, but the wave function will be so localized to the point that to such an extent that you cannot appreciate the spread because it's extremely small, and the wave function behaves for all practical purposes like a point. The cat is somewhere in space. Of course, the center of mass I'm talking about the center of mass of the cat. Then there is the internal structure. The center of mass of the cat is a point from the practical point of view, localized in space and moving according to Newtonian physics. You recover Newtonian mechanics as an approximation, an extremely good approximation at the macroscopic level. We can say that in a different way. We can say that the equation of collapse models is a kind of a solitonic equation. It admits a solitonic solution. Any initial state converges to a final solitonic state. The point is that at the microscopic level, the convergence is very slow and the soliton is very large. So you don't appreciate that it is a soliton, it is a wave. At the macroscopic level, when the mass is very large, the convergence is very fast and the soliton is very peaked around one point. And then you appreciate that it is a soliton. Okay, so this is the content. One important point, and I come to the third box, the box over here. What happens when you have situations when you have many atoms, but they are not in the superposition, all the atoms here plus all the atoms there. But each of them separately is in a superposition here plus there. So it's a microscopic superposition of many atoms, like in cold atom physics, in Bose-Einstein condensate. Well, in this case, even if you have many atoms, it's not a global superposition, but it's many times a single particle superposition. And then the collapse is ineffective. It's there, but it's very mild, very weak, and you can neglect it for all practical purposes. And this is important because now experimentalists are capable of creating such situations, and they can see quantum properties of these complex systems. And if collapse models kill the quantum properties, then they would be disproved experimentally. That is not the case. Okay, so this is how one should think about the collapse equation. It collapses the wave function, but the collapse is weak for microscopic system, and it's strong when you have a macroscopic superposition. So what happens? It's a question that typically people ask me. What happens to other degrees of freedom, momentum, spin, energy? Well, the situation is that when superposition, for example, in momentum, triggers a superposition in position, then the superposition dies. And this is the typical situation, because take a system which is localized in space, but in a superposition of two different momenta. After some time, because of the free evolution, the free quantum evolution, the superposition in momentum generates a superposition in position. The superposition in position is killed by the collapse process, and then indirectly, also the superposition in momentum is killed because also only this term survives. So in this situation, superposition in other degrees of freedom occur, and there is the classicalization of them. But for example, if you have a spin, so some internal spin superposition, which does not generate a superposition in position, then those superpositions are left unchanged by the collapse dynamics. So there is a preferred basis for the collapse, which is the position basis, because you want to recover classical physics. So these are collapse models. So there is, to summarize, there is the collapse of the wave function. The collapse occurs in space. It's effective only in some specific situations. In the other situations, it has only a mild effect. And everything is described by unique dynamical equation. So one question is, why should a wave function collapse? What is the origin of the collapse? So far, I only assume that linearity is violated, that the superposition principle, for some reason, is wrong at the fundamental level. But why should it be the case? Well, there is no consensus in the community why the wave function should collapse. We are not even sure whether these spontaneous collapses are really there in nature. But Penrose had an idea about that. And then that's why the Yoshi-Penrose model is famous. And so this is a picture taken from one of the slides of Roger Penrose. So he makes the following argument. When you have a superposition in space and you accept some quantum gravity model, even some basic model of quantum gravity, a superposition in space generates a superposition of mass, or a superposition of matter in space, generates a superposition of space-times. If I have the cat, the Schrödinger cat here, plus the Schrödinger cat there, then if I do quantum gravity, I will have a superposition of a little bump, a little curvature distortion generated by the cat here, and superimposed with a space distortion, a curvature here of space-time because of the cat being also there. So superposition in space generates superposition of space-time. And then Penrose says that the true quantum theory of gravity should not tolerate different superposition of different space-times, because you are not capable to uniquely define and the dynamical evolution. If you have a superposition of space-time, you cannot define a dynamical evolution for matter on space-time. Where should matter go? And then he says, for me, this is a hint that there is an instability, that the true quantum theory of gravity should not tolerate superposition of different space-times. The true quantum theory of gravity should be non-linear, should be a non-unitary, non-linear dynamics. So space-time doesn't tolerate superposition, so the superposition of different space-time is collapsed. And if the superposition of space-time is collapsed, then also the superposition of matter in space-time is collapsed, and you have this, and you have the collapse of the wave function. So that's the argument. He doesn't have a theory that does that, but he tries to build a phenomenological idea of how that should happen. And then Penrose suggests to use the time-energy uncertainty relation, that the decay of a superposition is just h bar over some energy quantity. And he quantifies the energy quantity as the gravitational content of the superposition. So like you have two classical parts, so like the cat being here and there, was like two cats being here and there, and they interact gravitation. So it's a gravitation, it's a Newtonian level, the Newtonian gravitational content of the superposition. And then if you plug numbers into it, you see that for a single electron or a single atom, the gravitational content is very weak, of course, and then the lifetime of a superposition is very long. But if you take, sorry, a macroscopic object, again, as I said before, the mass is much larger, the gravitational content is much larger, and the lifetime of a potential superposition is much shorter. And again, you recover what you want. Microscopic systems live long in quantum superposition, macroscopic systems do not. Okay, so these are ideas of Roger Penrose, and Dioschi was successful in, I go back, in proving that the model of Penrose can be implemented by a dynamical equation of this kind when taking G, the correlation function, as here in the bottom right of the slide. So Penrose had the idea, and Dioschi, actually before Penrose, implemented the idea in a dynamical equation, and that's why it's called Dioschi-Penrose. Okay, so this is the idea of collapse models, to break superpositions. Now the point is, so can we test this idea? Can we see whether they are right or wrong? I mean, a lot of mathematics have been done, a lot of models have been put forward, but the important question is, are they correct or are they wrong? Is the idea a correct idea, or is it just a nice mathematical idea but that nature didn't like? And so there is a lot of effort in trying to test these models experimentally, and you can test them because you modify the Schrödinger equation, so you make different predictions. Of course, these predictions are not crazy. They are tiny modifications of quantum predictions, but they are different, and so you can test them. And there are two ways of testing these models, and here I come to the second part of my talk. So the direct way, the obvious way, is to do interferometric experiments, to do the double slit experiment. So you take a particle, which ideally is as big as possible. You generate a superposition. You let the superposition live as long as possible. You try to isolate off sources of noise because you want to have a nice, clean experiment. And then you send the superposition through the double slit. And if in the back of the double slit you see an interference pattern like this one, then the wave was there. So there was no collapse of the wave function, and the models, collapse models, are wrong. But if the picture is something more like the one on the right here, where you do not see interference, then something went wrong. And then you have to understand what went wrong. Perhaps it was because of spontaneous collapses, or it was because of something else. But then it's research to be done to understand what is going on. So this is the direct way of testing these models, or of excluding them, or suggesting some possible violation of the superposition principle, which has always been done in the history of physics. When you want to see a wave nature, you do interference. The point is that with quantum system, it is very difficult to do interference, because it's difficult to control a massive particle, to keep it isolated from the surrounding environment. It's difficult to generate a superposition. It's difficult to keep it for some time. In general, it's difficult to control quantum properties for complex systems. Again, we can come to quantum technologies. Quantum technologies are nice, but it's difficult. It will be done, but it's difficult to scale them to more and more complex systems because of all the noises that are around. So people will do this kind of experiments. People are doing this kind of experiments, but will take several technological developments to make them extremely sensitive and to become real tests of collapse models. The other possibility is to do non-interferometric experiments. Non-interferometric experiments are based on the following important fact, that every time, and I try to present that in the picture, every time you collapse the wave function, you move the center of mass. This is something that it would take an entire talk only to explain why this has to be the case. So in this talk, and we will come out with a paper soon about that. But so at the moment, you just have somehow to accept this fact that every time you collapse the wave function, you move the center of mass. And since the collapses are going all the time, you constantly shake the system. So a collapse dynamics induces a diffusion, a Brownian motion on the quantum system. On top of the quantum diffusion, there is an additional collapse diffusion on the system. This is a prediction of collapse models. So instead of doing interferometric experiments, which are beautiful but difficult, you don't care about generating the superposition. You only try to monitor the motion of the particle very carefully and to see whether the motion is the one predicted by the Schrödinger equation or whether there is an additional motion due to the collapse of the wave function. And non-interferometric experiments are way more successful than interferometric ones. What are the advantages and the disadvantages? I already told them, but I want to summarize them. So the advantages of interferometric experiment is that they are a direct test of the quantum superposition principle. You make an interferometric experiment, you see interference fringes, there was a superposition. You don't see interference fringes, there was not a superposition. The difficulty is that the minus side, the disadvantage is they are very difficult from the technological point of view, not from the fundamental point of view. Non-interferometric experiments have the opposite virtues. So the disadvantage is that they are not a direct test of the superposition principle, but they are a direct test of collapse models, but not of the superposition principle. The advantage is that they are much easier to perform. So I like to make this analogy. It's like for gravitational waves. Gravitational waves were first seen with non-interferometric experiments when they saw the loss of energy due to the spiraling binaries in the 70s, so 50 years ago. They indirectly saw gravitational waves by seeing the loss of energy. The two binaries, they were spiraling around each other. They lost energy in terms of gravitational waves, and the loss of energy that were predicted by general relativity due to gravitational wave generation were matched with experimental evidence, and people won the Nobel Prize. But then it was important for LIGO to see gravitational waves directly with interferometers. So that's a similar situation. Non-interferometric experiments are simpler and they are important, but eventually you want to do interferometric experiments to see waves and to see interfere. Okay, so I will talk about non-interferometric experiments, which is what I've been working for the past decade or so. So we consider three strategies, three different platforms to test collapse models experimentally, which correspond to three different technologies, quantum technologies, which are very advanced quantum technologies. One is cold atoms, which is probably after quantum optics. Cold atom physics is the most important, together with the superconducting devices, it's the most advanced and most important quantum technology. So people now have reached an extremely high control of a cloud of cold atoms. They are capable of cooling the cloud to very low temperature, down to picokelvin, to some picokelvin. And then to see that the cloud freezes almost to that temperature. And then what happens? Now you can use this experiment to test these models, because according to these models, there is always an ongoing diffusion. So the cloud will not freeze so much. It will keep expanding because there are the noise, the collapses kicking the atoms around. And so you can see, you can check experimentally whether this extra diffusion is there or not. So cold atom physics to test collapse models. The other one is underground experiments. So here the situation is that if there is diffusion, so if the particle is kicked here and there around in space, and it is accelerated, diffusion is a type of acceleration. And if the particle is charged, it emits radiation. If you kick an electron or a proton, you also emit radiation. So collapse models predict that radiation should come out of matter, because matter is made of charged particles and matter is kicked by the collapse. Of course, this radiation is negligible. In most cases, it's the number of photons coming out is an incredibly small number, almost zero, but almost, not entirely zero. So you can think of doing high precision underground experiments to see single events, rare events, a photon coming out, one per day, one per whenever. And then to test the predictions of collapse models. This was a very successful experiment. I will tell you now about it. The other one is optomechanical systems. Optomechanical system, the prototype is a cantilever. There are many optomechanical platforms, but now let's consider a cantilever. It's an harmonic oscillator, a mass attached to a cantilever, which oscillates. It's an harmonic oscillator. You cool it, so it won't oscillate much. But according to collapse models, it should still oscillate more than what predicted by quantum theory. And then you monitor the mass of the motion of the cantilever, and you see whether the motion is the quantum one or whether it's the one predicted by collapse model. And again, this is another important quantum technology. A very precise oscillator, it's a force sensor. And actually, optomechanical devices are going also in that direction to become quantum technology as force sense. Okay, so first, the DP model, and then I will tell you about the CSL model, test of the DP model. So first, we tested the idea of DOSH-N Penrose. So first, a comment about the correlation function. So if you remember from the third slide of my talk or fourth, whatever it was, that the DOSH-Penrose model is like any collapse models, and the characteristic feature is that the correlation function is 1 over R. Well, there is a problem here from the mathematical point of view, that when you put 1 over R into integrals, you obtain infinite quantities. It's the typical divergences of the 1 over R potential in classical and quantum physics. So you need a regularization mechanism. You need to kill the high momentum components, or you have to suppress the small distances. It's the same thing. Let's make a cutoff at short distances. That's equivalent of giving an effective radius to elementary particles. So effectively, not fundamentally, effectively, in this model, the electron cannot be pointular. The proton cannot be pointular. We know the proton is not pointular. but even the electron is not point, like it has to have a finite radius. So actually there is an effective free parameter in the model, R naught. It's not really without parameters. The Diauchy-Penrose has an effective parameter. So what is the value of that parameter? Okay, here it's another long story. I cannot tell you about that. Penrose gave a specific prescription to uniquely identify the parameter. So it becomes again, the model becomes again without really free parameters, because for any physical situation, Penrose provides a prescription to compute R naught. So there is no free parameter. Diauchy instead followed a different route and will not tell you about here just for lack of time. Okay, so the point is about testing R naught then, the free parameter. So we did a work in testing this model, which appeared by now 2 years ago on Nature Physics. You have the reference over there. We computed the number of photons that should come out of charged particles according to the Diauchy-Penrose model. Again, collapses means shaking. Shaking is acceleration. Acceleration means that radiation comes out if the particle is charged. So we did I'm a theoretical physicist. We did the theoretical analysis. The group, the experimental group at the Gran Sasso laboratory did the experiment. We did the theoretical analysis, sorry, and the experimentalists did the experiment and the experimental analysis. So it's basically, it's a calculation about QED, to first perturbative order, of course. It's QED, you have a non-relativistic particle, you have a quantum, quantized electromagnetic field, the particle is subject to a noise, and then you do standard, I mean, it's not obvious, it takes some time, but it's a standard calculation. And then you get the formula in the box. The formula in the box is the number of photons coming out, which are predicted to come out of matter per unit time, so it's a rate per unit time, and per unit frequency omega. And on the right, you have the simplest version of the formula, which is to first perturbative order, and also within the range of energies which are indicated in the box. Otherwise, the formula is much more complicated. But this range of energy matched the one of the experiments, and so we were happy with this formula. And so you see there that all the constants of nature appear, all the constants of the model appear in the formula. You have E, the electric charge, because we are talking about photons. You have C, the speed of light, also because we are talking about photons. We have capital G, because it's the model that has that. You have R naught cube to the third power in the denominator, because again, it comes from the Diauchy-Penrose model. But you have capital N, which is the atomic number, and Na, which is the total number of atoms in the numerator, which tells you something important, that the more matter you have, the more photons should come out, of course. If you have more and more particles, there is higher chances that at some point a photon comes out. So the rate is proportional to the size of the object that you are considering the experiment. It's inversely proportional to the energy omega k, which means that in principle, it's favorable to do the experiment for small energy, for low energies, because the rate is higher. But actually, it's better to do it for high energies, where the rate is lower, but you have a much better control of the experiment. In the X-ray region, there are very sophisticated experiments to detect also few photons. In the low energy region, the experiment is not as clean. And that's it, basically. So that's the theoretical formula. So what does the experiment say? The experiment has been done in the Gran Sasso laboratories, which you see in the right. So this is a view from above of the facility. It's an underground, it's inside the mountain. So these are the external buildings, but the really laboratories are underground. And here in the middle, you see the picture of the inside of the laboratories. And on the left is the schematic of the experiment. It's basically, it's a piece of ultra pure germanium, and you just wait for photons coming out and to detect photons. And then here you have all the details, but it's not so much important. So this is the experiment. And this is the experimental result. So here in the, oops, sorry, wrong. Here in the histogram, so the black curves here is the data taking. So the data taking period was 62 days, so 2 months. For 2 months, the experimentalists waited for photons coming out depending on the energy. The energy goes from 1,000, it's keV, yes, 1,000 to 3,500 keV. So from 1 to 3.5 keV, sorry, not 1,000, from 1 to 3.5 keV. So this is the data taking for energy with the error bars, of course, it's a Poissonian process. And then what happens then? So this is the experiment. They saw, and this is, this part, the part here is only a subset of the entire spectrum that was taken. So the entire spectrum is the one on the bottom right. The green part is the one that it was of interest. And then what happens here? That you have to do data analysis. So many of these photons coming out can be accounted for, can be explained because of some processes occurring inside the detector. The detector is not perfect. Always there is some noise that disturbs and generates a signal, like radioactive process, whatever it is. So there is over the years, experimentalists did a full characterization of the detector, and they know that some photons will come out, some X-rays will come out anyhow, because the detector is not perfect. And the green histogram is the characterization, is the number of photons that were accounted for because they know that the detector works that way. So out of the 576 photons signals that they saw, almost all of them, 506, were explained because of the internal mechanism of the detector. So there were already only few photons. In 2 months, they saw only 500 signals, and most of them were expected. So only basically 70, I mean, in a statistical sense, were unexplained, which is a low number. So they could have come from collapse models, they could have come from some other process which has not been considered before. But the point is that the collapse of the wave function cannot be too strong. It cannot predict more than 70 photons in that time, because if it predicts more than 70 photons, then the model is wrong, because people didn't see much more than 70. So the only 70 are unexplained, and you cannot predict more than that, because not more than that were seen experimentally. And so you put a bound on the model, on the strength of the model, and then the parameter R naught sets the strength of the model. The smaller R naught, if you remember in the theoretical formula, it was in the denominator. So if R naught is small, the collapse effect is strong. The prediction is higher. If R naught is large, the collapse is weaker, and the prediction is smaller. And then here you have the possible values of R naught. And then the green line is the exclusion region. R naught cannot be smaller than this number here between 10 to the minus 11 and 10 to the minus 10 meters. It cannot be smaller than that, because if it were smaller than that, the model would have predicts more photons than what has been seen experimentally. So the model is wrong. And the red and the blue one were previous experimental evidence. So you see that our model, our experiment, improves previous results by 1, 2, almost more than 2.5 orders of magnitude. And this was sufficient to exclude the model, because according to Penrose, according to the Penrose, the theoretical value of R naught should have been here. I wish I could tell you why, but it would have taken too much time. So the idea of Penrose predicts the value of R naught to be here. But all these data, all these numbers are excluded experimentally. So this is unfortunately, it would have been nicer to see a positive result, but we saw a negative result. That the first model, so the simplest version of this model has been killed experimentally. Then you can refine the model. Now I don't want to spend too much time here. You can improve the model without doing crazy things. But it's the first situation, the first time where one of these models was excluded. So what about the CSL model, the other model? And now I'm going towards a conclusion. The CSL model has 2 parameters, so not only one. 2 parameters, and then you have to do a 2-dimensional diagram. You have R naught here, RC here, and lambda here. These, the black bullets here are some theoretical guesses put forward by Adler and by Gherardi, Ribini, and Weber over the years. The gray area is a region that you exclude for theoretical reasons, the gray area. Here in this region, the parameters, the value of the parameters are too weak, and they would make the model ineffective. The model would be simply useless in collapsing the wave function. So you don't want the values of the parameters to be too weak. And in fact, the black bullets are above the gray area. Now, experiments will constrain the models from above, because if you go up here, the values of the parameters are very strong, the prediction very large, and if it's too large, it's excluded by experiment. And in fact, now we see, and I go towards conclusion, we see what experiment says. This is the cold atom experiment that I told you before, the cloud of cold atoms that freezes and it expands always a little bit, but not too much. And then this orange area is excluded, because in this orange area, the values of the parameters would make the expansion larger than what's seen experimentally. So this is wrong. Then X-ray, the experiment I told you before, you can apply the X-ray experiment also to collapse models, and you kill this extra region. You can do optomechanical system. These are gravitational wave detectors, Auriga, LIGO, LISA, Pathfinder. In all these systems, they are classical, but optomechanical system where you have a mass, the mirror of LIGO, which should not move much. But according to collapse models, it should move a little bit, because inside the mirror, the protons are collapsed, and then the center of mass moves. And then you kill all this region on the left. You see that you kill all this region. And then you can do really the microscopic cantilever. This is a very small mass. You can see here, you see this line here is 50 micron. So the little ball here, it's basically 1 micron, whatever it is. It's a very microscopic ball attached to a cantilever that vibrates. And then you kill this region in the middle. Or if you do an improved version, you kill this region over here. And then if you take recent experiments, you go even down this way. And here, this year in Nature Physics, we made a review of all these experiments. You can find it in Nature Physics. And so basically you see now that there is this white region which is left, which still is, it looks small in the picture, but there are still how many orders of magnitude? 4, 5, 6 orders of, it's still a big region. But now it's a region, focused region, where the collapse dynamics might be right or might be wrong if excluded, but gives a clear indication to experimentalists where to look to search for possible deviations of the quantum superposition principle, which is one of the most important challenges in the foundations, to understand whether the quantum superposition is right or wrong, because on that our understanding of quantum world is based, and also quantum technologies heavily depend on the unlimited, the scalability of quantum technologies depends on the unlimited validity of the quantum superposition principle. Okay, so if you want to explore this region, then you have to do a lot of technological developments, and possibly you have to go to space, possibly. And that's why we wrote this, we worked on the space version with also a comment on nature and a research paper on communications physics. That's where you possibly have to go to space if you really want to go down. That tells you that these are extremely challenging experiments. Okay, so I'm at the end of my talk, and it's been almost 1 hour, basically. So I thank you for the attention, first of all. I want to thank you, my research group and the founding agencies.
So thank you very much for this very exciting and deep talk. That was a pleasure to listen. So can we now take some questions? Angela, can we now take some questions?
Yeah, sure, yes.
Indeed, there are some questions in the chat. Can you read them?
The chat. The first. Okay, so I asked first in the chat. So how that stochastic terms and nonlinearity and definition of the theory relates with chaotic behavior and Lyapunov stability? Is the theory predicting a quantum chaos? So okay, so no, these are two different things. These are so if you do a quantum chaotic theory, basically. So sorry, I rewind. At the moment, there are two different things. So one cannot exclude that in the future there will be some relation, but at the moment there are two different things. So in quantum chaos, basically, you have a complex system, and then you study how it chaotically behaves, and you have the Lyapunov stability and these kind of things. Here, instead, it's basically a classical noise, so it's just stochastic process. It's a classical noise applied to a quantum system, and there is no chaotic behavior. It's a stochastic behavior, but it's not in the technical sense a chaotic behavior. Actually, it's a very well-defined behavior. It's a solitonic behavior of the system. So at the moment, there is no relation among the two. That doesn't exclude it in the future. When we understand more about these models, you will see that there is actually a relation. Okay, so I hope I answered the question. The other question is just a curiosity: what are the dark count rates in the experiment? What kind of photon detectors are used? Okay, oh no, this is a very experimental question. This is so. This is I don't know what the photon detectors are. So it's it's a germanium detector. That's the best I can tell you. This is a germanium detector, and the photons that are detected are X-rays, and the dark counts rates, I don't know. Sorry, I did a theoretical part, so I apologize I cannot answer the experimental question. It's in the paper, so I have just to ask the person who raised the question to have a look at the paper. Okay, so this is okay. Again, yes. So I want to ask experimental aspects. I'm sorry that I cannot answer the experimental aspects in a proper way. So what is the plus that our experiment to be a direct test of both collapse models and superposition principle? Don't that superposition principle work and only? I'm not sure if I understand this question. So again, I recall gravitational waves. So for me, one could say that when they saw this loss of energy in the rotating system, the binary system, there was a claim that they saw the gravitational waves. But still, it was important to test them directly. I think it's a kind of a partly psychological, partly physical thing to see something directly and not indirectly. So I would say that so I think that it's nothing more than that. Doing a direct experiment of superposition is preferable with respect to the indirect experiment, even if the indirect experiment is equally conclusive. What about non-gravitational collapse models? Well, the CSL model is a non-gravitational collapse. The CSL model has no relation to gravity. So the collapse doesn't have to be related to gravity. It could be related to some other source. CSL is one of that examples. So your photon counting seems sampling of very rare events. Oh yes. No. So certainly it's a very rare event. That's certainly for sure. And that's so you really just count it. Basically, there was how many photons per day? So 570 over 2 months. So you can divide it by 60. So it was 10 counts per day. So 1 every 2 hours. So it was extremely rare event, and the experiment is designed to do that. And is there any trick that you apply to enhance the sampling? No. And so basically, there are only 2 possibilities. You take a larger system. So, but then you have to have it. So other experiments have a bigger sample. So, but the germanium detector that was available at the Gran Sasso was that one. It's not easy to buy new ultra pure germanium and make a new detector, because you also have to characterize it again. So if you change the detector and increase, you have to characterize it from scratch. So you can do it, but it takes time and work. Or the other thing is just to wait longer. The more you wait, the more photons you should see, and the better statistics you have. These are the two possibilities. Okay, so I hope I answered the question on the chat. And I can take some live, of course. You're welcome. So there are some raised hands. Okay, yes.
Please.
So Solomon, no? Solomon Samuel.
Yes,
I see you.
Sorry, I couldn't unmute myself earlier. Thank you for this really nice talk. It was very inspiring. I have two questions. So my first question is just as an example, so I get a bit of better idea maybe how your model works. So say we have a particle and it passes through a detector, and for that duration that it passes through the detector, we see some trajectory. It interacts and we can see some of the trajectories, and then it will pass on, it will go on. So just according to this model, what do we see there? What happens to the I mean, how does the trajectory that we actually can observe classically appear according to this model? That's the first thing I want to ask. And I will
let me ask
after the answer.
Yes, I prefer to answer one question at a time. Well, so just to understand, so if you are talking about a detector that generates a trajectory, because not all detectors generate a trajectory. Some detectors they just give a click. So you could have, for example, one detector here, one detector there. The particle is the superposition, and then you see this one clicks or this one clicks, and then you say the particle is here, the particle is there. So in this case, you do not see a trajectory, you just see here or there. So if you are talking about a detector that generates a trajectory, it means that there is a detector that is continuously monitoring the motion of the particle. Like, I don't know, I mean, you are a young guy. I don't know if you've ever seen these old pictures of the bubble chambers that were used in the 50s or in the 70s. This bubble chamber, and you see the bubbles that reproduce the trajectory. There you have a continuous measurement of the position, and then from the very beginning you measure and you collapse the wave function. So here the wave function collapses at the very beginning, and then it's like a classical thing. The collapse occurs immediately at the very beginning, and then it's basically just a classical dynamics. The particle keeps going on like a classical particle because it's already been collapsed at the beginning. I don't know if this answer your first question. You are muted.
Sorry, I muted it and I couldn't unmute again. That partly answers it. So the reason I asked is because I was always wondering whether the existing quantum mechanics, including the complexity of many body systems and the many body dynamics, maybe could explain why the collapse happens. That's why I asked whether there's a special thing about the model that you have that helps. So the second question I wanted to ask is...
Can I comment before the second question? Because it's important, can I comment on this? So you're telling whether standard quantum mechanics with the complexity of the situation can explain the same thing. It's basically the coherence it is. Now, here it's a crucial thing. This is an important thing in the foundations. So if you apply the argument, can you kill the microphone? Sorry, because there is a lot of noise. Can you shut the microphone off? There is a noise coming from the room. So the situation, the thing is important here. So if you tell that the system plus the complexity of the environment explains the situation, you are making a division between system and environment. That is an arbitrary division that you're making because you are assuming that you are an external observer observing the situation and deciding that the particle is important for you and the environment is irrelevant. And again, you have this mysterious division. If there is no observer and there is hypothetically a universe where there is only the particle and the chamber and the environment, and there is no one making any division, It's just a unique quantum system in a unique, crazy, highly entangled, highly non-classical situation. So on the practical level, what I want to say is that on the practical level, if you want to do calculations, yes, the coherence and the complexity of the system explains the classicality. But at the fundamental level, you want to go really to the foundation, say, but is the particle behaving like that? Because that is the dynamics of the particles, independently of me talking about system, environment, complexity, and whatsoever. The answer is no, because the fundamental level is a unique, crazy wave function. There is nothing classical in that wave function. In the model I'm studying, it's not that. At the fundamental level, the wave function collapses. At the fundamental, not practical level, at the fundamental level collapses. And the fundamental dynamics is nonlinear. And then you don't have this crazy superposition anymore. It's not a practical difference, it's a fundamental difference at the moment.
Okay, Özgür Hocam, please.
Thank you. Thank you so much, Angelo. It's great to see you. And
My pleasure to see you again.
See you as well. My question is about, I want to hear your opinion about the recent reports, experimental and theoretical reports from the Vlatko Vedrel and collaborators about this entanglement of living bacteria with photon, and they could see quantum entanglement at quite a large macroscopical object like a bacteria. So my speculation will be, if this is consistent with a collapse theory, can we say that such bound objects have lower effective mass because of the contribution of atom, and the photon makes some reduced mass, and then it becomes consistent with collapse theory? I wanted to hear your opinion about this this direction of research.
So I don't remember. I don't remember about the experiment actually, but it was at the microscopic level. It was not a large mass. So so photons basically don't collapse. So you can apply collapse models, but even for a vastly large number of photons, the collapse is so weak that it can be basically set to zero for all practical purposes. So when photons are involved, forget about the collapse. And then in the massive system, I don't think it was not a macroscopic superposition. It was, and therefore collapse models are not excluded by that type of experiment.
I see. So the bacteria masses, when entangled with photons, it is effectively mass is low and it's still considered microscopic, right?
Yes. Yes, it's so there was a quantum feature, but it was still a microscopic one. It was not a macroscopic. It was not that because of the photon, the bacteria went in a superposition here plus there. This is the kind of things that are important for classicality. If the internal state of the bacteria or a part of it, it's quantum, then it's a microscopic quantum, and we know it's a quantum world.
I see. Okay. Thank you. I wanted to hear this from you. Okay. Yeah. Thank you so much.
Sure. My pleasure.
Angelo, thank you so much for these discussions and talk. You mentioned about our postponed school on March, quantum photonics. And now I see on the wall in front of me the poster of the school, and I hope we will come together face to face at this.
I hope so.
As soon as the pandemic situation will allow us to come together. So
I really hope so. And thank you for the invitation again.
Yeah. It was a great pleasure to have you with us. Thank you once again.
Thank you very much again for the possibility to give a talk for everybody who participated, for the questions, and see you soon then in person.
Yeah, sure.
Okay, bye-bye. Bye.
Bye.